So we just got done talking about how ionic compounds dissolve in water, and you were exposed for the first time to solubility rules, which takes the ideas of lattice energy and puts them into kind of an organized table so you know whether or not you've got strong lattice energy or weak lattice energy. Remember that if you have strong lattice energy, the ionic substance is going to stay held together. Water will not be able to dissolve it. If you have something with a weak lattice energy, water, the attraction of the ions to water is actually stronger than the attraction of the ions to the other ions in the ionic crystal. And so water is able to actually pull that crystal apart and it dissolves. So in order for various ionic compounds to mix with each other, what we need to do is dissolve them in water. Ionic substances actually don't interact with many things unless they're dissolved in water when their ions are free to move. If you have an ionic crystal that's a solid, the ions are kind of stuck in place. They can't really do much to react. And so you saw that in the lab when we were doing conductivity. Solid ionic crystals didn't conduct because those ions were not free to move. However, you dissolve those ionic compounds in water, separate the cations and the anions from each other, and now they are free to move. So in order for ionic compounds to mix or to interact, they have to be separated. So we're going to take a look at what's going to happen when an ionic substance mixes with another ionic substance. And like I said, the only way for that to happen is through solutions. So when we start off, you're going to do a lot of these activities. So when we start off, both reactants are in separate dropper bottles typically. And what are they going to look like? So let's say that we're doing the reaction potassium phosphate and what shall we do? Magnesium chloride. Let's do those two things, okay? So there's our formula, potassium phosphate and magnesium chloride. So if I have potassium phosphate in water, these guys are both soluble. So what's going to happen? I've got potassium ions and I've got phosphate ions. And I have them at a ratio of 3:1 because that's what my formula says I need in order to keep it neutral. So my solution needs to be electrically neutral as well. So for every 1 phosphate, I need 3 potassiums. Likewise, magnesium chloride is soluble in water, so what do I wind up with? I wind up with magnesium ions, which are 2+, and chloride ions, which are Cl-. So this is really what my ionic compounds look like in water before I mix them. Okay, so now I'm going to mix them together, and what's going to happen? Well, if there's no reaction, the ions are simply going to stay separate. So I would have K+, phosphate ions, magnesium ions, and chloride ions all mixed up together. There would be no attraction between this guy and that guy, this guy and that guy, that guy and that guy, and likewise anywhere else. That may or may not be true in this case, so I'm going to put kind of a question mark because I'm going to look at solubility rules to help figure it out. If there is an attraction between two of the ions, what will happen is those ions will start to stick together. And again, we're going to use the lattice energy to figure that out. So what we need to do is think about, well, what will happen? So if I have potassium, we already know that I can separate it from phosphate because we know that's how it started out. It started out dissolved in water. Is potassium and magnesium ever going to be attracted to each other? Hopefully you say no, because they're both cations. Why would they be? So the only other question is, will potassium be attracted to chloride strongly enough to form a precipitate? So once again, we're going to get out our solubility rules. Well, chlorides are soluble except for silver and lead, but also we know potassium is one of the alkali metals. So either way, we know that potassium chloride is not going to be attracted strongly to each other either. So now we've got to look at the magnesium. Once again, we know magnesium is not strongly enough attracted to chloride because we were able to get it to dissolve. But what about magnesium potassium? We already know that's not going to happen. So what about magnesium to phosphate? If we put magnesium phosphate together, what's going to happen? So once again, we're going to go to our solubility rules, and you're going to see that phosphates are insoluble except those covered by Rule 1. Well, magnesium is not part of Rule 1. Magnesium is an alkaline earth metal. So what's going to happen is magnesium and phosphate are going to be really strongly attracted to each other. And that makes sense because look at their charges, +2 and -3. So what's going to happen is you're going to start to get a crystal forming of magnesium phosphate. Now I'm going to keep this very simple and just write alternating cations and anions. But this is what's going to happen. The ions are going to start sticking together. And I start to create a crystal that eventually will fall to the bottom of the beaker. So I get this solid crystal forming. And again, it's three-dimensional. Okay, but what about potassium and chloride? Well, they just stay floating around. They don't do anything. So when you mix two ionic compounds together, what you're really doing is if I go back to this side, you're really looking at what happens if I take the cation from one and interact it with the anion of the other. If I take the cation from one and interact it with the anion of the other, will I get a strong enough lattice energy between those opposite pairs to create a crystal? So once again, solubility rules are going to help you. So here's my prediction. So we're going to practice with this. I'm going to do 2, and then you guys are going to get a chance to do 2 and practice a little bit. So lithium phosphate, I know, is Li3PO4. Calcium acetate, CaC2H3, O2, 2. Okay. If I have 2 solutions of these guys and I mix them together, what's going to happen? Well, calcium would combine with phosphate, lithium would combine with acetate. So I would get lithium acetate and calcium phosphate. So now what I want to do is I know these guys are soluble. All the reactants are always going to be soluble because otherwise there would not be a reaction possible. But I want to look at the solubility rules for those 2 precipitates. So lithium acetate, lithium, all acetates are soluble except silver, plus lithium is an alkali metal. So for sure, we know that this is going to be soluble. So some people will write soluble, some people will write AQ for aqueous. Calcium phosphate. Phosphate rule, if you remember, all phosphates are insoluble except those covered by Rule 1. Calcium is not part of Rule 1, so this guy is going to be our precipitate. This is insoluble, and so it wouldn't be aqueous, it would be solid. S for solid, AQ for aqueous. Okay, so how about these guys? Partnering up, barium would go with the opposite anion. Potassium would go with the opposite cation. So what are my 2 possibilities? Barium, I'm running out of room here. Not writing straight. Barium sulfate and potassium nitrate. Okay, so once again, use your solubility rules. Sulfates are insoluble except those of barium, strontium, and lead. Calcium are moderately soluble. So barium is an exception. So barium sulfate is going to stay soluble. Potassium nitrate, gosh, if you don't have to memorize these rules, but the one rule you'll probably memorize is nitrates. All nitrates are soluble. Easy rule to remember. So no matter what, soluble. So am I going to see a crystal, a precipitate form here? Nope, because both of them are soluble. Okay, so now pause for a minute and finish the other 2, and we'll come back and check and we'll see where you're at. Okay? Okay, so hopefully you've gone through and predicted what the products will be and whether or not they're going to be soluble. So for this third reaction, sodium chloride and magnesium carbonate, hopefully you know without looking, this guy's going to be soluble. So that guy will be aqueous. Magnesium carbonate, carbonates are insoluble except those covered by Rule 1. So that's going to be a solid. So there's a precipitate. And then if we go to the last one, lead acetate and ammonium chromate, lead 4 acetate is going to produce lead 4 chromate, plus 4 minus 2. Hopefully it's pretty obvious that that guy is definitely going to be a solid. So he definitely will be a precipitate, but solubility rules support that idea. And then ammonium acetate, acetates are soluble, ammonium salts are soluble, so we know this guy's going to stay aqueous. All right, so you've got some practice with solubility rules. You've got some practice with predicting insoluble products via combinations of ionic substances. You've got some homework to do, so check your assignment sheet for that, and the topic will be done.